Hello guys, it's Color from 19. Mm, it's day 5 in my challenge day, and today I'm gonna learn explanation for vectorization implementation and iteration functions, and about why do we need non-linear activation functions like value rectified linear unit function and derivatives of activation functions and gradient descent for neural network and so on. And it's 7:30 a.m. and I will keep this recording until 8:30.
In the previous video, we saw how with your training examples stacked up horizontally in the matrix X, you can derive a vectorized implementation for propagation through the neural network. Let's give a bit more justification for why the equations we wrote down is a correct implementation of vectorizing across multiple examples. So let's go through part of the forward propagation calculation for a few examples. Let's say that for the first training example, you end up computing this x1 plus b1, and then for the second training example, you end up computing this x2 plus b1. Um, and then for the third training example, you end up computing this x3 plus b1. So just to simplify the explanation on this slide, I'm going to ignore b's. But let's just say, to simplify this justification a little bit, that p is equal to 0. But the argument I'm going to lay out will work with just a little bit of a change, even when b is non-zero. This just to simplify the description of this slide a bit. Now, W1 is going to be some matrix, right? So I have some number of rows in this matrix. So if you look at this calculation, x1, is that W1 times X1 gives you some column vector, which is draw like this. And similarly, if you look at this vector X2, you have that W1 times X2 gives some other column vector, right? And that gives you this, I guess, C12. And finally, if you look at X3, you have W1 times X3 gives you some third column vector. That's this C13. So now, if you consider the training set capital X, which we formed by stacking together all of our training examples. So the matrix capital X is formed by taking the vector X1 and stacking it vertically with X2, and then also X3. This is if we have only 3 training examples. If you have more, there'll be a keep stacking horizontally like that. But if you now take this matrix X and multiply it by W, then you end up with, if you think about how matrix multiplication works, you end up with the first column being these same values that I had drawn up there in purple. The second column will be those same 4 values, and the third column will be those orange values, whatever they turn out to be. But of course, this is just equal to Z11 expressed as a column vector, followed by Z12 expressed as a column vector, followed by Z13 also expressed as a column vector. And this is if you have 3 training examples. If you have more examples, then there'll be more columns. And so this is just a matrix capital Z1. So I hope this gives a justification for why when we had previously W1 times Xi equals C1I, when we're looking at a single training example at a time, when you took the different training examples and stacked them up in different columns, then the corresponding result is that you end up with the z's also stacked up in columns. And I won't show, but you can convince yourself if you want that with Python broadcasting, if you add back in these values of b, that the values are still correct. What actually ends up happening is you end up with Python broadcasting, you end up adding bi individually to each of the columns of this matrix. So on this slide, I've only justified that Z1 equals W1X plus B1 is a correct vectorization of the first step of the 4 steps that we had on the previous slide. But it turns out that a similar analysis allows you to show that the other steps also work out using very similar logic, where if you stack the inputs in columns, then after the equation, you get the corresponding outputs also stacked up in columns. Finally, let's just recap everything we talked about in this video. If this is your neural network, we said that this is what you need to do if you were to implement forward propagation, one training example at a time, going from I equals 1 through m. And then we said, let's stack columns like so. And for each of these values, C1, A1, Z2, A2, let's stack up the corresponding columns as follows. So this example for capital A1, but this is true for Z1, A1, Z2, and A2. Then what we showed on the previous slide was that this line allows you to vectorize this across all n examples at the same time. And it turns out with a similar reasoning, you can show that all of the other lines are correct vectorizations of all four of these lines of code. And just as a reminder, because x is also equal to a0, because remember that the input feature of vector x was equal to a0, so xi equals a0i, right? Then there's actually a certain symmetry to these equations where this first equation can also be written z1 equals w1 a0. So you see that this pair of equations and this pair of equations actually look very similar, but just with all of the indices advanced by one. So this kind of shows that the different layers of a neural network are, roughly doing the same thing, or just doing the same computation over and over. And here we have a two-layer neural network. When we go to a much deeper neural network in next week's videos, you see that even deeper neural networks are basically taking these two steps and just doing them even times than you see here. So that's how you can vectorize your neural network across multiple training examples. Next, we've so far been using the sigmoid function throughout our neural networks. Turns out that's actually not the best choice. In the next video, let's delve a little bit further into how you can use different what's called activation functions, of which the sigmoid function is just one possible choice. When you build your neural network, one of the choices you get to make is what activation function to use in the layers as well as at the output units of your neural network. So far, we've just been using the sigmoid activation function, but sometimes other choices can work much better. Let's take a look. Steps for the neural network, we had these two steps where we use the sigmoid function here. So that sigmoid is called an activation function. And here's the familiar sigmoid function, a equals 1 over 1 plus e to the negative c. So in the more general case, we can have a different function, g, of z, which I'm going to write here, where g could be a function that may not be the sigmoid function. So for example, the sigmoid function goes between 0 and 1. An activation function that almost always works better than the sigmoid function is the tanh function, or the hyperbolic tangent function. So this is z, this is a, this is a equals tan h of z, and this goes between +1 and -1. The formula for the tan h function is e to the z minus e to the negative z over their sum, and is actually mathematically a shifted version of the sigmoid function. So as a sigmoid function just like that, but shifted so that it now crosses a 0, 0 point and e scale, so it goes between -1 and +1. And it turns out that for hidden units, if you let the function g of z equal to tan h of z, this almost always works better than the sigmoid function, because with values between +1 and -1, the mean of the activations that come out of your hidden layer are closer to having a 0 mean, or 0 point minus e to the 1. An activation function that almost always works better than the sigmoid function is, so for example, plus e to the negative z. So in the more general case, we can have a different function g of z, which I'm going to write here, where g could be a nonlinear function that may not be the sigmoid function. So for example, the sigmoid function goes between 0 and 1. An activation function that almost always works better than the sigmoid function is the tan h function, or the hyperbolic tangent function. So this is z, this is a, this is a equals tan h of z, and this goes between +1 and -1. The formula for the tan h function is e to the z minus e to the negative z over their sum, and is actually mathematically a shifted version of the sigmoid. So as a sigmoid function just like that, but shifted so that it now crosses a 0, 0 point at V scale, so it goes between -1 and +1. And it turns out that for hidden units, if you let the function g of z be equal to tan h of z, this almost always works better than the sigmoid function because with values between +1 and -1, the mean of the activations that come out of your hidden layer are closer to having a zero mean. And so just as sometimes when you train a learning algorithm, you might center the data and have your data have zero mean, using a tan h instead of a sigmoid function kind of has the effect of centering your data so that the mean of the data is closer to zero rather than maybe 0.5, and this actually makes learning for the next layer a little bit easier. We'll say more about this. The second course when we talk about optimization algorithms as well. But one takeaway is that I pretty much never use the sigmoid activation function anymore. The tanh function is almost always strictly superior. The one exception is for the output layer, because if y is either 0 or 1, then it makes sense for y hat to be a number that you want to output that's between 0 and 1 rather than between -1 and 1. So the one exception where I would use the sigma activation function is when you're using binary classification. You might use the sigmoid activation function for the output layer. So G of C2 here is equal to sigma of C2. So what you see in this example is where you might have a tan H activation function for the hidden layer and sigmoid for the output layer. So deactivation functions can be different for different layers. And sometimes to denote that the different activation functions are different for different layers, we might use these square bracket superscripts as well to indicate that g of square bracket 1 may be different than g of square bracket 2. And again, square bracket 1 superscript refers to this layer, and superscript square bracket 2 refers to the output layer. Now, one of the downsides of both the sigmoid function and the tanh function is that if z is either very large or very small, then the gradient, the derivative or the slope of this function becomes very small. So if z is very large or z is very small, it's a 0. So this will slow down gradient descent. So one other choice that is very popular in machine learning is what's called the rectified linear unit. So the value function looks like this, and the formula is a equals max of 0 comma z. So the derivative is 1 so long as z is positive, and the derivative or the slope is 0 when z is negative. If you're implementing this, Derivative when z is exactly 0 is not well defined, but when you implement this in the computer, the odds that you get exactly z equals 0.00000000000 is very small, so you don't need to worry about it. In practice, you could pretend the derivative when z is equal to 0. You can pretend it's either 1 or 0, and then your code will work just fine. So the fact that it's not differentiable, the fact that so here are some rules of thumb for choosing activation functions. If your output is 0, 1 value, if you're using binary classification, then the sigmoid activation function is a very natural choice for the output layer. And then for all other units, ReLU, or the rectified linear unit, is increasingly the default choice of activation function. So if you're not sure what to use for your hidden layer, I would just use the ReLU activation function. It's what you see most people using these days, although sometimes people also use the tanh activation function. One disadvantage of the ReLU is that the derivative is equal to 0 when z is negative. In practice, this works just fine, but there is another version of the ReLU called the leaky ReLU. We'll give you the formula on the next slide, but instead of it being 0 when z is negative, it just takes a slight slope like so. So this is called the leaky ReLU. This usually works better than the ReLU activation function, although it's just not used as much in practice. Either one should be fine, although if you had to pick one, I usually just use the ReLU. And the advantage of both the ReLU and the leaky ReLU is that for a lot of the space of z, the derivative of the activation function, the slope of the activation function is very different from 0. And so in practice, using the ReLU activation function, your neural network will often learn much faster than the sigmoid activation function. And the main reason is that there's less of this effect of the slope of the function going to 0, which slows down learning. And I know that for half of the range of z, the slope for ReLU is 0, but in practice, enough of your hidden units will have z greater than 0, so learning can still be quite fast for most training examples. So let's just quickly recap the pros and cons of different activation functions. Here's the sigmoid activation function. I would say never use this except for the output layer if you're doing binary classification. I mean, almost never use this. And the reason I almost never use this is because the tanh is pretty much strictly superior. So the tanh activation function is this. And then the default, the most commonly used activation function is the ReLU, which is this. So if you're not sure what else to use this one. And maybe, feel free also to try the leaky value where um, might be 0.01 C commas, right? So A is the max of 0.01 times C and C. So that gives you this bend in the function. And you might say, why is that constant 0.01? Well, you can also make that another parameter of the learning algorithm. And some people say that works even better, but I hardly see people do that. So, but if you feel like trying it in your application, please feel free to do so, and you can just see how it works and how well it works, and stick with it if it gives you a good result. So I hope that gives you a sense of some of the choices of activation functions you can use in your neural network. One of the themes we'll see in deep learning is that you often have a lot of different choices in how you build your neural network, ranging from number of hidden units to the choice of activation function, to how you initialize the weights, which we'll see later. A lot of choices like that. And it turns out that it's sometimes difficult to get good guidelines for exactly what will work best for your problem. So throughout these few courses, I'll keep on giving you a sense of what I see in the industry in terms of what's more or less popular. But for your application, with your application's idiosyncrasies, it's actually very difficult to know in advance exactly what will work best. So a common piece of advice would be, if you're not sure which one of these activation functions work best, try them all and evaluate on like a holdout validation set. Or development set, which we'll talk about later, and see which one works better and then go with that. And I think that by testing these different choices for your application, you'll be better at future proofing your neural network architecture against the idiosyncrasies of the problem as well as evolutions of the algorithms, rather than, if I were to tell you always use a value activation, don't use anything else, that just may or may not apply for whatever problem you end up working on, either in the near future or the distant future. All right, so that was a choice of activation functions, and you see the most popular activation functions. There's one other question that sometimes I get asked, which is, why do you even need to use an activation function at all? Why not just do away with that? So let's talk about that in the next video, and where you see why neural networks do need some sort of nonlinear activation function. Why does it neural network need a nonlinear activation function? Turns out that for your neural network to compute interesting functions, you do need to pick a nonlinear activation function. Let's see why. So here's the four prop equations for the neural network. Why don't we just get rid of this? Get rid of the function g and set a1 equals z1. Or alternatively, you could say that g of z is equal to z. Right? Sometimes this is called the linear activation function. Maybe a better name for it would be the identity activation function, because it just outputs whatever was input. For the purpose of this, what if A2 was just equal to Z2. It turns out if you do this, then this model is just computing y or y hat as a linear function of your input features x. To take the first two equations, if you have that a1 is equal to z1 is equal to w1 x plus b, and if then a to z2 is equal to w2 a1 plus b. Then if you take this definition of a1 and plug it in there, you find that a2 is equal to w2 times w1x plus b1 is the bit, right? So this is a1 plus b2, and so this simplifies to w2 w1x plus w2 b1. This it's just let's call this w prime b prime. So this is just equal to w prime x plus b prime. If you were to use linear activation functions, or we could also call them identity activation functions, then the neural network is just outputting a linear function. It's networks with many, many layers, many, many hidden layers. And it turns out that if you use a linear activation function, or alternatively, if you don't have an activation function, then no matter how many layers your neural network has, all it's doing is just computing a linear activation function. So you might as well not have any hidden layers. Some of the cases that I briefly mentioned, it turns out that if you have a linear activation function here and a sigmoid function here, then this model is no more expressive than standard logistic regression without any hidden layer. So I won't bother to prove that, but you can try to do so if you want. But the take home is that a linear hidden layer is more or less useless because the composition of two linear functions is itself a linear function. So unless you throw a nonlinearity in there, then you're not computing more interesting functions even as you go deeper into the network. There is just one place where you might use a linear activation function, g of c equals z, and that's if you are doing machine learning on a regression problem. So if y is a real number, so for example, if you're trying to predict housing prices, so y is not 0 or 1, but it's a real number, anywhere from, I don't know, $0 is the price of a house up to how expensive, right? Houses can, I guess, maybe houses can be, potentially millions of dollars. So, however, however much houses cost in your data set, but if y takes on these real values, then it might be okay to have a linear activation function here so that your output y hat is also a real number going anywhere from minus infinity to plus infinity. But then the hidden units should not use linear activation functions. They could use ReLU or tanh or leaky ReLU or maybe something else. So the one place you might use a linear activation function is usually in the output layer. But other than that, using a linear activation function in a hidden layer, except for some very special circumstances relating to compression that we want to talk about, using a linear activation function is extremely rare. Oh, and of course, if you're actually predicting housing prices, as we saw in the week one video, because housing prices are all non-negative, perhaps even then, you could use a ReLU activation function so that your outputs y hat are all greater than or equal to 0. So I hope that gives you a sense for why having a nonlinear activation function is a critical part of neural networks. Nick, that if you functions or w prime p prime, so this is just equal to w prime x plus p prime. If you were to use linear activation functions, or we could also call them identity activation functions, then the neural network is just outputting a linear function of the input. Um, We'll talk about deep networks later, neural networks with many, many layers, many, many hidden layers. And it turns out that if you use a linear activation, don't have an activation function, then no matter how many layers your neural network has, all it's doing is just computing a linear activation function. So you might as well not have any hidden layers. So The cases that I briefly mentioned, it turns out that if you have a linear activation function here and a sigmoid function here, then this model is no more expressive than standard logistic regression without any hidden layer. So I won't bother to prove that, but you can try to do so if you want. But the take home is that a linear hidden layer is more or less useless because the composition of two linear functions is itself a linear function. So unless you throw it, when you implement backpropagation for your neural network, you need to really compute the slope or the derivative of the.
Okay, then I'm going to recap today of what I learned. The sections what that I learned is explanation for vectorized implementation and activation functions in your network, and about the why do we need a nonlinear activation functions in our network. So to justify the vectorizing implementation in your network, we can just align these components, uh, computations for each component, and then we can simply justify how this vectorizing form is right or not. So it was kind of easy problem. And about the activation functions, we've been used so far sigmoid function to for logistic regression. But there are also a hyperbolic tangent function, which is mathematically is equal to a shifted version of sigmoid function. And it turns out that is always better than sigmoid function. And but about the output layer in binary classification, we just need to we need to use sigmoid function because our output label will be 0 or 1, and also our prediction, which is y hat, is also ranged from 0 to 1. But if we use tanh function for output layer as an activation function, it will be ranged -1 to 1. So it is not fit into our problem. But these both functions has a huge downside because when their g is called very big or very small, like here and there, the gradient will be so changes so slow like this. Even though you go further, following the g axis, but as you can see, the gradient seems not change anymore. So it can make your network to learn slower than any other good activation functions. So instead of using that, we can use a ReLU function, which is called a rectified linear unit function. It actually has a zero value when the g is smaller than 0, and when the g is bigger, greater, or equal than 0, it is equal to y is equal to x form, which is called identity function. So there is a varied form of ReLU function, which is called leaky. value. Um, and it has a slight gradient when the g is smaller than 0, unlike the value function changes it just 0. Because value function can have a mm, huge difference in gradient based on its g value. So for example, when the g is smaller than 0, it always fluctuates the gradient based on the g value. So our neural network can learn more faster in practice. For last, the um, the reason that we need a nonlinear function, nonlinear activation function in neural network, because as you can see, if we just substitute our activation function as a linear function, we can see that the previous layer just stack into next, and we can just uh, extract out of these W1 and B using a linear closure property. And as you can see, we can just substitute these W2 and W1 superscript and B1 auxiliary. To as of some kind of W, prime and B prime. And hence that is just a linear equation again. So conclusion is that it always be one hidden layer, regardless of how much hidden layers we actually have in our network. So it turns out that it can be much less useless in the neural network in practice. So that's all for this today's recording, and thanks for your watching.